Jackson. Jackson, you there?
Hi, David. Yeah.
How are you doing today?
Pretty good. How are you?
Good. I got these 3 worksheets,
Yeah.
but I was wondering if you want the answer to part D on this question.
Yeah.
Okay. Remember how I did this? I tried to draw the function from the graph of the first derivative.
Mm-hmm.
Okay? And after I did so, I tried to determine whether that point is less than that point or that point. Okay? Because we won't know if it's an absolute minimum unless I can be certain that this point over here isn't below it. Well, it occurred to me after thinking about it for a while, and this is very fundamental to integral calculus. What happens if I start at that point and I look at the derivative? This tells me that I'm going to be increasing from -5 to -3, right?
Yep.
What rate am I going to be increasing? Well, I start out with low slopes. I get up to a slope of 1, and then I get back to low slopes. So I couldn't be going up very much vertical distance. The distance between there and there can't be that far. Okay? Now once I get to -3, the first derivative is negative from -3 to 1. So it has to be falling from that point to this point. And the question is this distance that it falls greater than the distance that this rose? And the answer is yes. How do we know? The area of that semicircle versus the area of this semicircle. This semicircle being much bigger area basically tells you that this function falls a greater amount between -3 and 1 than it rose between -5 and -3. Okay? And then from 1 to 4, it's increasing, so clearly this is moving up by an amount of the area of that triangle. And then it finally turns back down again, but that's a very small amount to turn down. It's this distance right here, and that's clearly not going to be the same as this distance here. So that puts this point, f of 1 being 3, as the absolute minimum. And the reason this is a great problem, it took me a while to realize how good this problem was, is that it introduces you to the concept that the area under the curve is important. It's meaningful. The area of this space right here is a measurement of how far up the original function moves. And the area under the curve is a measurement of how far down it moves, and so forth.
Okay.
Let's look at this stuff that you sent me today. Which one is the first one here? Is this it?
Yeah.
Okay, and I think this was my image 1, yeah.
So I just circled some problems to go through.
Okay, which ones?
So 1 we can start with.
Okay. Find A and B so that the graph of that has a relative minimum at 2, 1. Okay, what's obviously the first thing we need to do?
You find the derivative of that?
Yeah. Okay. Now, they're saying that there's a relative minimum when x is 2 and y is 1. So y prime has to be 0 when x is 2. So that's one equation.
Yeah.
And if, okay, and we also know from the original function that 1 equals a times 2 squared plus b times 2 plus 3. So there's going to be our second equation. So what does this give us? 1 equals 4a plus 2b plus 3. So 4a plus 2b equals minus 2. Okay. Now we have two equations and two unknowns, and we can solve it. Let's put both equations in standard format, and we're going to use elimination to solve it. There's the first equation. Second equation is 4a plus 2b equals minus 2. How do I solve that?
Well, I would just say 4a equals minus 2 minus 2b, and then you can plug that in for 4a, right?
Well, that'd be using substitution,
Oh,
but it's really much easier to use elimination. Let's subtract the two equations, and that'll get rid of the a. Okay, so if I can add or subtract any equations, well, I'm going to subtract them. Now I have b minus 2b, which gives me that. And I have 0 minus a negative 2, which gives me that. So that tells me b is equal to minus 2. And if b is equal to minus 2, then a must be equal to plus 1/2. Plugging b into that equation and solving for a. So we have a equal to 1/2, b equal to minus 2. Now let's just do a quick check as to whether that point works. When x is 1, we have 1/2 minus 2. Let's see. No, excuse me. When x is 2, we have 4 over 2. So we have 2 minus 2. No, minus 4. That's a negative 2 plus a 3 gives you positive 1. So it satisfies, that solution satisfies that equation. And
okay.
that's all I feel a need to satisfy. Okay? So, do you see how we did this? How we came up with two equations? In other words, the whole goal is you got to come up with a second equation. You can never solve one equation and two unknowns.
Yeah, I was just confused on where your second equation came from, but
I was a little when I first looked at it also. But if we just plug in these 2 points for x and y, then we have our second equation that's going to be an equation of A and B.
All right. And then also circle number 2.
Okay? Okay. So we have this equation that's not defined in terms of y. And in fact, you'll notice that it would be very difficult to solve for y. So what are we going to do? They're talking about the equation of the tangent line, which always involves slopes. Slopes are first derivatives. So let's solve for dy dx.
Okay.
You have to do it implicitly. Implicitly differentiate this thing.
So,
in other words, whenever you run into an x, you can treat it like explicit differentiation. Whenever you run into a variable other than x, you have to follow it with, in this case, a dy dx. So first of all, use the product rule.
okay.
So we'll start way over here on the left. It's 2x times the derivative of y. What's that?
You just put y prime?
Yeah, okay. Are you comfortable with that notation?
Yeah.
Okay. Plus, what's the rest of the power rule?
Y times 2. Or
2y. 2 times y. And there we don't need a y prime because we didn't take the derivative of y. We took the derivative of 2x to get the 2. Okay? So we applied the product rule there. That's what we got. Now, implicitly differentiate that.
That'd be, is it 4y, y prime?
It's 4y cubed.
Oh, and then
In
y?
other words, then y prime.
Okay.
In other words, you have to take the derivative of the outside. You just have to follow it with a dy dx. Okay? And I can differentiate the left side only if I differentiate the right side. What's the derivative of the right side?
2x.
Okay? How do I solve for y prime?
Hold on.
Think algebra. Think gathering like terms and putting everything else on the other side of the equation.
You divide by?
Not yet. Let's gather all of our y prime terms.
So you could subtract 2y.
Well, let's just do it one step at a time. There's our y prime terms. I'm going to leave those on the left side of the equation. Everything else, I'm going to move to the other side of the equation. With me? You see how I got that?
Mm-hmm.
Now the key step is factoring, as it frequently is in math. I want to factor out a y prime. Since that's all equal to 2x minus 2y, so all I have to do is divide both sides by that coefficient, and I've solved for y prime. So my y prime is equal to 2x minus 2y all over 2x plus 4y cubed. And 99% of the time when you do implicit differentiation, you end up with the first derivative being a function of both x and y, not just x. When you explicitly differentiate something, you usually end up with an answer that's just a function of x, but not with implicit. Okay? But remember these two steps, because these are the two hardest steps that everybody has difficulty with. In other words, gather, you're trying to solve for y prime, so any term that has y prime in it, leave it on one side of the equation, and every term that doesn't have it in it, take it to the other side. Then factor out the y prime, then divide by the coefficient, you have your answer. Now, use the equation of a tangent line. Well, when the x-coordinate is 1.9, thinking for a moment. There's this point over here. That point is on that curve. So what's the equation of the tangent line going to be?
Y minus 1.
Good. No. Let's give the general formula. Y minus y sub 1 equals what? Slope.
M
Slope.
times x minus x sub 1.
Okay, there you go. That's going to be the equation of the tangent line. Well, we know what m is. It's that. Okay? And we know what y sub 1 is. It's 1. And x sub 1 is 2. So let's do some plugging in here and see what we have. We have y minus 1 equals, what's the slope? 2x minus 2y. Let's see, I can divide top and bottom by 2 there. So I can simplify that a little bit. That's x minus y all over x plus 2y cubed. X plus 2y cubed. That's the slope. And x minus 2 is the x point. So use this equation to approximate the y coordinate when x is 1.9. Which means that if we substitute x equal 1.9 here and solve for y, we will have our answer. Not that that's going to be very easy to do. Is this the linearization method? Yes, it is. Notice that x being 1.9 is very close to x being 2. In other words, I know that when I substitute x of 2, y is 1. So what's y going to be when I substitute something close to 2? Well, hold on. I need to open my calculus book here. There is a formula for this. I just don't use it often enough to have it memorized. This is also, this is the linearization. I need to look that up. Linear approximation, 235. I think I'm missing a step. Yeah, using the tangent line approximation. Let's go back a moment here. What we get, to use the tangent line approximation, you do this. Okay, So that's the formula that's going to let us approximate that. Okay, so C being the 1.9.
Okay.
So let's see if I can remember how to do this. F of C is going to be F of trying to think for a moment whether C, hold on, I'll get here. Yeah, C is 2 here. So we have F of 2, which we know to be 1, right?
Uh-huh.
Plus F prime of 2. That's not so easy, because F prime ends up being a function of x and y. Perhaps I can substitute the x value of 2 and the y value of 1 to solve for f prime of c. It probably is what I want to do. In other words, if I substitute 2 and 1, what do I have? 2 minus 1 all over 2 plus 2. So I have 1/4 is f prime of c. So that's 1/4 times 2 minus 1.9, which is 0.1. And I know that f of 2 is 1, so I have 1 plus 1/4 of 0.1, which is 0.025. So that is the approximate value of y when x is 1.9. In other words, if I were to graph that function on Wolfram alpha, I would see that it was decreasing as I went into the point 2, 1, because when x is less than 2, y is greater than 1. It's 1.025.
Okay.
I think I did that right. I'm a little bit, I would need to spend a few more minutes reviewing it to make sure I got this part right. But this looks right to me. To calculate f prime of c, you have to, if you've implicitly differentiated, you have to use both points, the x and the y point.
Okay.
All right, we got 5 more minutes. Which one would you like to look at?
17 for the next page.
Okay, you can do this one fine. You know how to sketch the graph of the derivative of this?
Yeah.
Okay. Pretty easy to sketch the derivative of a function. What's more difficult to do is to sketch the graph of f of x.
Yeah.
That's a little hard to do. So doing this is a little bit like the problem we started with today. You needed to graph the original function based on the graph of the derivative. But I'll do whatever you want. Which page? Or which number?
The next page, there's 17.
Find the minimum and maximum points on that graph. Okay, let's talk about the strategy we're going to use. What are we going to do? In other words, I'm not sure we have enough time. I don't mind going over a little bit if you want. But how are we going to solve it? I think we can talk generally here.
Yeah. You can just take the derivative, right?
Right. How are you going to take the derivative?
Use implicit.
Right. Let's do it real quick. Have you implicitly differentiate that. Let's make sure you can do that. So implicitly differentiate the left side.
So 2x plus 8y y prime minus 2, that'd be minus 16
y prime.
y prime.
Yep, because that's a variable that's not x.
Okay.
So whenever we run into a variable that's not x, we got to follow it with a dy dx. Or if that were an r, we'd have to follow it with a dr dx. Okay? And that's all equal to 0. In other words, the 13 goes away, the 0, you still have to take the derivative of the right side, but it becomes 0.
Mm-hmm.
Okay, now what's the next step?
Set that greater than 0 and less than 0.
No. We've got to solve for y prime.
Oh, yeah, sure.
In other words, you can't set y prime equal to 0 until you've solved for it.
Okay, so
What's the very next step, and it's the most important step?
group the y primes together.
Okay, so what's the next line?
So I wrote y prime and then parentheses 8y minus 16.
All right, so you're doing both steps at once. You're factoring out the y prime. The only thing you have to be a little careful with here is you don't mess up this sign. In other words, when you multiply these two back together again, make sure you get that term and that term.
Mm-hmm.
Okay. Move everything else to the other side of the equation, which becomes what?
2 minus 2x.
Okay. Now what?
And then you would divide.
And then simplify. I can divide top and bottom by 2. So there's y prime. They want to know where maximum and minimum points are on this thing. Well, it's where y prime is equal to 0. So now I have 1 minus x over 4y minus 8 equals 0. How do I solve that? What has to be true for that to be equal to 0?
The numerator?
Yes, that's the only thing you care about. Doesn't matter what the denominator is, the numerator has to be 0. So x has to be 1. So that's the only place where the first derivative is equal to 0. So if we're looking for relative minimums and maximums, well, they don't say relative. They say find the maximum and minimum points on the graph. Well, we have found something that's definitely a maximum or a minimum. Okay? We can figure out what it is if we wanted to apply the first derivative test. In other words, test to the left and right. It's going to be a maximum if the slopes go from positive to negative. It's going to be a minimum if the slopes go from negative to positive. But there's something else we have to do. This might be the only answer. In other words, normally I have found the only point on this graph that has a flat tangent line. You can't have something be a minimum or a maximum unless it has a flat tangent line or it's an end point. Well, there's no endpoints here. They didn't specify an interval. If they'd have said on the interval from -5 to +5, well, then I would need to check those endpoints and see what the y value is at the endpoints. But they didn't specify that. So the endpoints, the only maximum or minimum is going to come where that first derivative is equal to 0. And we just showed that that's at x equal 1, and that's the only place. There's no other way you could have a maximum or a minimum. In other words, let's just, I won't keep you any longer than this, but does this curve have a maximum and a minimum?
Yes.
No.
No.
Its maximum is infinity, which means it does not have a maximum. Its minimum is negative infinity, which means it does not have a minimum. So infinity doesn't count. So if you get a curve that's constantly, in other words, if I have a parabola, well, that doesn't have any maximums, but it does have a minimum right there. That's its minimum value. And it comes when x is equal to that value right there. So I don't know what kind of curve this is. Oh, yes, I do. That's an ellipse. Now, hold on a minute. How do I know that's an ellipse? Because I have an x squared plus a y squared with a different coefficient. All this, we're going to complete the square to figure out the ellipse, which means that if I were to graph that in Wolfram alpha, might look something like that. So we should have, look, my minimum and maximum occur at the exact same spot. That's where x equals 1. We have both a maximum and a minimum at x equal 1. I'm glad I looked a little further at that. It's important to realize that's the equation of an ellipse. Because once I realize that, I know that that x equal 1 is not just a maximum or a minimum, it's both. Even if the ellipse is a vertical ellipse, wouldn't matter. I have found that the flat tangent line comes when x equals 1. And I get both a minimum and a maximum at that.
Okay.
Okay? All right, Jackson, I'll let you go. Are we meeting Friday, or do you not need a Friday session?
I think I can do Friday.
You want to do Friday?
Yeah.
Okay, from 12 to 1?
Yep.
Talk to you then.
All right. Thank you.
You're welcome. Bye-bye.